Hi, and welcome back to another edition of Easy Theory. So today we're going to look at this exam problem from way back in 2006 on the GATE exam. And we did this on a recent live stream in office hours, and I thought it was interesting enough to make a video about. So what we have here is we have the language L, which is corresponding to this regex right here. And we note that the alphabet has just the character 1, which is going to actually be crucial here. And what is the regex? It's the star of this inner regex, which has 3 ones union 5 ones. And because it's a regex, therefore L is a regular language, and there is a DFA for it. I guarantee that. Now the $1,000,000 question is on here is what is the minimum number of states for a DFA for L? So obviously there is a DFA, so there is a minimum number of states, but we have to determine what the minimum number is. So if you have an idea of how to solve it, please pause the video before continuing and put down in the comments if you have a particular way of solving it. So what I want to do is I want to show you 2 ways of doing it. So note, this question was on a test, and it's one of many questions you have to answer. So the time spent to try to solve this question shouldn't take very long. So what we're going to do is we're going to have 2 different approaches for this. One which is the very basic approach, and one which is a little bit more clever and is a lot faster. So we note that this is a regex. So the slow way we can go about doing this is we have this regex right here, and we can just convert it to an NFA, and then convert the NFA into a DFA, and there is a very simple algorithm to be able to minimize any DFA. And then we can, at that point, minimize that DFA. So let's try doing that. So if in the conversion from a regex to an NFA, we really should be precise here, but for the purposes of just finding the minimum number of states, the NFA that we get out of this doesn't matter, as long as we get a regex. We get an NFA for this regex. So I'm just going to make this quick, and what I'm going to do is I'm going to have a little NFA that recognizes 3 ones only. Then I'm going to make an NFA that recognizes exactly 5 ones, like this. And then to get the union, we need to make a new start state and epsilon our way to the old ones. And to get the star, we need to make a brand new start state over here and have the old start states epsilon their way to the new start state so that we can go through the machine again. And this clearly is an NFA for it. So now we just got to convert this thing to a DFA. So what I'm going to do is I'm going to name all these states Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, Q9, Q10, Q11. So to convert this to a DFA, we have to find the epsilon closure of the start state, which is Q0, Q1, Q2, Q3. Everywhere we can go from Q0 on epsilon transitions. So I'm going to make a state called Q0, Q1, Q2, Q3. So note that this DFA is going to be quite big, so just be prepared for that if you're going to actually do this yourself. But the good thing to note here is that the alphabet only has 1 character, so every state is only going to have 1 transition corresponding to it, which is kind of nice. So Q0 and Q1 have no 1s coming out of... actually, I should have noted that that's an epsilon transition, but it doesn't really matter here. So Q0 and Q1 don't really do anything for us right here. So Q2 and Q3 on input 1, where do they go? They go to Q4 and Q5. So I'm going to make a state Q4, Q5, and now we got to figure out where that goes on 1. Well, and note that there's no epsilon transition in these 2 states, so we don't have anything to do with epsilon closure. So what do we do here? Well, Q4 goes to Q6 on 1, Q5 goes to Q7 on 1. and there's no epsilon transition from these two states right here. So I'm going to make a state Q6, Q7. Now we got to figure out where this goes on 1. Now is where things get interesting. Well, Q7 can go to Q9, so we have to include Q9 here. But Q6 can go to Q8, but Q8 can go to all these other states, namely Q0, 1, 2, and 3, via epsilon transitions. So the set of states we can reach are Q0, Q1, Q2, Q3, Q8, Q9. So it's a rather big state. And I always write them in ascending order like this so I can keep track of which states I've seen already. And if I make a state like this that I've already seen before, then I just go back to it. Okay, so now we go here. So Q0 and Q1, again, do nothing for us. Q2 and Q3, we'll have Q4, Q5 listed. Let's see, Q8 goes nowhere on 1. Q9 goes to Q10. So Q4, Q5, and Q10 are the 3 states that we can reach. Now we got to figure out where we go on 1. Well, let's see. Q10 is going to go to 11, 0, 1, 2, and 3, just like before. So of Q0, Q1, Q2, Q3. The 4 and the 5, like before, go to Q6, Q7. So we have Q6, Q7. And of course, the 10 gives us Q11. And the good thing is that the only epsilon transitions that exist in the machine are in involve these 4 states right here, and these epsilon ones that go back. There are no epsilon transitions in the middle, which is nice. Okay, so what about on this transition? Well, Q0 and Q1 do nothing. Q2 and Q3 go to 4 and 5. Q6 and Q7 go to 8 and 9. So notice that we have 6 and 7 here. They go to 8 and 9. Well, 8 goes to 0, 1, 2, 3. So I have to have 0, 1, 2, 3. And then Q8, because that's what Q6 went to. Q7 goes to Q9. And Q11 goes nowhere. So this is the state that we have now. I promise we will close up pretty soon. So then now let's have another transition. So again, 0 and 1 do nothing. 2 and 3 give us 4 and 5. Q4 and 5 give us 6 and 7. 8 goes nowhere. 9 goes to 10. Let's just make sure I got that right. Yep, that's right. 3, 4, 5, 6. Yep, so that's fine. So now let's look at the 1 transition here. So the 10 gives us 11, 0, 1, 2, 3. So here we have Q0, Q1, Q2, Q3. Oh, that's not the entire state. Q4 and Q5 go to 6 and 7. So Q6, Q7. Q6 goes to Q8. Well, so then we have to include Q8 in the list, but it doesn't really do anything for us otherwise because it'll go back to 0, 1, 2, 3, but we've already included 0 through 3. Let's see. We handle 6 and 7. Well, Q7 goes to 9. So Q9. Q10 goes to 11. Well, but that doesn't do anything for us here. So again, it's a huge state listing. Then on 1, where do we go? 0 and 1 do nothing. 2 and 3 take us to 4 and 5, just like before. Actually, we're going to make some more room. So Q4, Q5. 6 and 7 will take us to 8 and 9. Well, that includes 0 through 3 again. So we have to include that. Q2, Q3. Then we have Q8, Q9. And then let's see. So we did those two. 8 goes nowhere, 9 goes to 10, and also 11 goes nowhere. So we have Q10 here. And I don't think we've made that state yet. Nope, we haven't. 5, 6, 7, 8, 9, 10. Yep. So then let's look at the transition here on 1. So we should be closing up pretty quick. So Q0, Q1 do nothing. 2 and 3 give us 4 and 5. 4 and 5 give us 6 and 7. Let's see. 8 goes nowhere. 9 goes to 10. And 10 goes to 11. So we have Q10, Q11, and also 0 through 3. Yep, that's right. And then now let's look at the 1 transition here. So 2 and 3 give us 4 and 5. 4 and 5 give us 6 and 7. Q6 and Q7 give us 8 and 9, so then that gives us 0 through 3 again. So 8 and 9. 10 goes to 11. Yeah. Let's just make sure I got that right. Yep. 4, 5, 6, 7, 8, 9, 10, 11, 12. Actually, let's just make sure I didn't make a mistake, because I don't want to make a mistake here. So 0 through 3, those go to 4, 5, 6, 7, 8, those go to 8 and 9. Well, 8 gives us 0 through 3, so we have 8 and 9. 2 and 3 give us 4, 5. 8 goes nowhere, 9 gives us 10, yep. 0 through, so then we go to 11, 10 gives us 11, which gives us 0 through 3. 4, 5 gives us 6 and 7, yep. So then 2 and 3 give us 4 and 5. 6 and 7 give us 8 and 9, which gives us 0 through 3. Q11 goes nowhere, so we got this state. So you notice that this is not the intended path of solving this, right? So 2 and 3 gives us 4 and 5. 4 and 5 give us 6 and 7. 8 goes nowhere. 9 gives us 10, and that's good. Yeah. Then 4 and 5 gives us 6 and 7. 6 and 7 give 8 and 9, which gives us 0 to 3. 10 gives us 11, but that doesn't really help otherwise. On 1, so 2 and 3 give us 4 and 5. 6 and 7 give us 8 and 9, which gives 0 through 3. 11 goes nowhere. 8 and 9 give us 9 and 10. Yep. Actually, let's see. 9 gives us 10. Yeah. 6 and 7 gives us 8 and 9. 8 goes nowhere. 9 gives us 10. Yeah, okay. So that's good. 2, 3 gives us 4, 5. 4, 5 gives us 6 and 7. 8 goes nowhere. 9 gives us 10. 10 gives us 11, which gives 0 through 3. And then, let's see. 2, 3 gives us 4, 5. 4, 5 gives 6, 7. 6, 7 gives 8, 9. 8 gives us 0 through 3. 10 gives us 11. 11 goes nowhere. Yep. So it's worth checking out. Checking whether this is right. Okay, so then now let's see. 2, 3 gives us 4, 5. 4, 5 gives 6 and 7. 6, 7 gives 8 and 9, which gives us 0 through 3. 9 gives us 10. And 11 goes nowhere, I think. Yep. Holy moly, this is a big thing. So then 2, 3 gives us 4, 5. 4, 5 gives us 6, 7. Hopefully this closes off quickly. 8 goes nowhere. 6 and 7 gives 8 and 9, which gives us 0 through 3. 10 gives us 11. Oh, do we have that already? Oh, we don't have that already. Oh wait, no. Yes, we do. Ah, it was the previous state. Ah, that's nice. Excellent. So this comes back on 1. That's a big DFA. All right, so now the one thing that we need to do is to find the final states. Well, the ones that include the final states are Q0, 8, and 11. So if it has a Q0, 8, or 11 in it, then we're good. So this one's final. 4, 5 is not final. 6, 7 is not final. This has a Q0 in it. The next one's not final. The next one is final because it has a Q0. This one has a Q0. This one is not final. And we can see why, because the string to get to this state is of length 7. And it's not possible to get 7 via combinations of 3 and 5. And that's actually important for later. This one's final because there's a 0 in it, 0 in it, 0 in it. In fact, all of these are final. So what you can actually realize here is that we can actually minimize this DFA pretty easily, because from this state, once you get here, you'll never leave a final state. So to minimize this, what I can do is I can just cross out all these other states and put a self loop on 1 here. And I can claim that this DFA right here is minimal. Why? Because there's only 1 character in the alphabet. So if it weren't minimal, then that means that some earlier state in here will have to either self-loop on 1 or go to another earlier state on 1. Because otherwise this would be the minimum size DFA anyway. Well, that doesn't work because this state right here is final. Not final. So if we went back, then what we could potentially do, if I put a self loop here, then I wouldn't get longer strings. But if this were a final state, then I would accept the string of length 7. So, which we shouldn't do here. So actually, the minimum number of states is 9. And so what is a faster way of actually proving this? Because this was actually really, really time consuming, and it didn't really give us any insight into the problem. Because all we're really doing here is we're just applying the existing algorithms, and it doesn't really tell us anything interesting. So here's the interesting thing. So what we're really doing here is, because there's only 1 character in the alphabet, I don't care what the strings are themselves. I just care what the numbers are. So what we're really asking here is, what is the smallest number that cannot be represented using a combination of 3 and 5? Because the strings that we're dealing with here are of length 3 and 5. So what we're really asking is, what is the smallest number that can't be represented using those numbers? And the minimum number of states then is 1 more than that number. So, is that actually right? Actually, no, it's 2 more, I think. Yeah. It's 2 more. Because the string of length 0 we need to consider. So it's actually 2 more than this. So let's actually think about this. Well, can I get 0 from any combinations of 3 and 5s? Well, yes. So 0 is okay, because I can just choose 3 and 5 0 times. 1 is definitely not possible, because I need to pick something from here, and I can't pick a string of length 1. Same thing for 2. 2 is not possible. 3 is possible, because I can just pick the thing of length 3. 4 is not possible, because if I pick the 3, then I can't pick a 1. If I pick the 5, that's too much. I can pick the 5, because I can just pick it once. I can pick the 6, because I can just choose the 3 twice. I can't do 7, because if I pick the 3, then I need to get 4 more, but we already showed that 4 is not possible. If I pick the 5, that means I would need to pick 2, but 2 is not possible. 8 is possible because I can pick 3 and 5. And then now, once we get to 8, what we can do is, can we get 9 and 10? So if we can get 9 and 10, I claim we can get every number afterwards. So if we can get 9 because I can pick 3 times, so that's possible. I can get 10 because that's 5 twice. So 10 is possible. And now notice what's happening here. I have a consecutive run of 3 numbers that I can all get. So that means that if I wanted to get 11, all I need to do is just to get the one for 8 and add the 3 string onto it, which I can do because of the star here. So this actually tells us that once we get to 8, we're completely good, and we can get every string afterward. And we can actually notice that here, I can get 0, I can't get 1, I can't get 2, I can get 3, can't get 4, can get 5, can get 6, can't get 7, and every number after 8 I can always get. Isn't that really, really beautiful? How this problem about like DFAs really tells us something interesting about combining numbers together, about what is the largest number that you can get without, or at least not get, with a combination of 2 numbers. And we can ask the same question about like maybe 4 and 7, or 2 and 11, or something. So the great thing is that we can always get that this number is finite. So you may think, okay, well, what is the largest possible number I can't represent here? Well, the answer is it's always finite. No matter what 2 strings I put here, it's always finite. Why? Because this is a regex, which means that there's a DFA for it, and if you minimize the DFA, the number of states is related to the largest number you can't represent. Isn't that just absolutely beautiful? Ah, wow, I love that question. It's just so beautiful. Okay, cool. So if you're able to show this a different way, I would love if you can share it with us in the comments below. But otherwise, I love solving that. I have office hours every weekend on Saturdays and Sundays, 2 p.m. GMT for 2 hours. You can ask questions, and you can see something like this, something that beautiful unfold. If you want to support the channel, please like and subscribe to the channel. It costs nothing, and it really helps with the YouTube algorithm. And as always, I will see you next time.